We didn't wait for the bell this time because we just thought we'd start. So my name's Declan. I come from Australia. I'm from the CSIRO. I also want to thank my other co-authors who did the majority of the work. And today, my timer, I'm going to talk about E. coli attenuation, which you probably think isn't that interesting. So I hope you like statistics, okay? Because there's going to be a bit of statistics. So, firstly, in Australia, a lot of MAR is regulated by E. coli. So they measure E. coli and everything. And look, I know E. coli is only an indicator, and I know that viruses can travel further in the wastewater, in the aquifer. We all know that. And I know that in terms of doing a quantitative microbial risk assessment, the bacteria are probably the least risk. But our regulators still use E. coli because it's a simple, cheap, and simple and cheap indicator of, process control and microbiological quality. So I'm going to take you to, hopefully, there is two. Okay, this is Perth over here, this area here, all over Western Australia. And we looked at data from 17 full-scale treated wastewater infiltration sites, MAR. So pretty well all of Western Australia, which is, come on. Oh, this is frustrating. All of Western Australia, which is the state on the left, is a very sandy, and they basically infiltrate all of their wastewater and disposal via sandy infiltration basins. They also, incidentally, use MAR for their drinking water supply, and by 2020, 20% of their municipal drinking water supply of a town of 2 million people will come from treated wastewater MAR. But the majority of it is still just disposed of or reused for irrigation, and I'm going to talk about 17 full-scale operational sites that have been going for 50 years or so. So there's a lot of data for some of them. Now, firstly, does anyone know what censored data is? Boris, you'd know, right? You don't know? Okay, so censored data. It's something that people don't do well in generally when they look at statistics. So censored data is, so if you think of E. coli, you have some sort of detection limit here. That worked, fantastic. And typically you get a heap of values where you actually measure, but you get a value and it's below the detection limit. And a lot of people don't know how to deal with that data. And then you get a whole heap of other detectable values up on a range. So for E. coli, in this study, we have a detection limit of less than 10 E. coli per 100 mil. So often, people will cheat statistically and fraudulently and either replace it with a 0 so they can use it in their statistics, or they might use half the detection limit, so it would be 5 in this case. I'm telling you can't do that. That is fraud, and it's the old way of doing things. I'm going to show you how you can deal with this sort of data statistically. I'm going to use E. coli as an example because it's the example I have. So that's what the left censored data looks like. If you had it above a detection limit on this side, you can have right censored data. So it can go either way. And in fact, it will in this presentation. So here's the data we have. This is the E. coli inputs for 17 pond or activated sludge wastewater treatment plants when they go into a pond infiltration system. And you can see, here's our detection limit of 10. Of course, most of them are way above because this is secondary treated wastewater or activated sludge, and you'd expect them to be high. You'd have an average of, between 160, which seems really low, to 24,000, which seems more right, I think, for this sort of type of stuff. That's how systems work. But what I want to show is there's a spread here. You can see the median values here in the box plots going all the way up. They're just listed by their values. There's a couple of outliers, and they're all over the place. It wasn't that pond or activated sludge systems cluster nicely together. That's number one. You can also see it has an upper reporting limit. I don't know why it really has an upper reporting limit. Maybe they're a bit lazy in the end of the laboratories, where they're counting for anything bigger than 24,000 is just reported as greater than 24,000. So the question remains, how do you deal with data that is either above or below a detection limit? And that's really what I'd like to talk a bit about today, as well as show, because it has a value, right? It has information content in that measurement, and often that's just thrown away, and people don't actually realise it's pretty useful. So you have a distribution. For those of you who understand distributions, we'll have a distribution of values, and for left censored data, it'll be this things here, below a detection limit. So each time you can actually, if you imagine, still fit a distribution to a series of points that are censored, even though you don't know what's on the left of that. You can use all the other points, the other side, or the non-censored points. So, I don't know if people know, but a lot of water quality parameters in water are usually log normally distributed. So not normally distributed like these ones, but actually log normal, which is lowest value 0, they have a sort of average value, then they have a really long tail of going out to high values. So, firstly, if anyone hasn't been to WA, Western Australia, the reason we do this work is because it's a really nice coastline and we want to protect the seals. So really they're looking at, I guess, the environmental risks and understanding this is what we're looking at, and this is why we need to protect our environment. But just behind the seal, you'll see there are a couple of, this is just I'm going to give this as an example of the 17 sites, but you can do it for any of them. You can see they've got some ponds, maturation ponds, and a series of infiltration basins, and the seal would live here. We have some monitoring bores, background bores, and we're going to see how the E. coli travels in the subsurface, and does it get to the end, or how many log removals do you get. So we're using, like I said, I've got a full paper. You can read the details if you're interested. I'm going to use this example all the way through, and I'll give a summary of the rest of them. So it has an average discharge of 715,000 metres cubic per year. I don't know if that's a lot, but it sounds like a lot. So, probably people don't normally look at their data this way. I'll have to explain it. Firstly, this is just EC data, okay? Electrical conductivity. We've got the input water, this one here, and you can see it's log distributed. I've tried to fit a log line. Doesn't fit well, this one, but it works better with E. coli. We've also got, I have to go back and see what the bore is. Probably 297, 197. So 2 bores, or 697. So this one here, it's terribly fitted with the diamonds there, and also this one is the background. I guess the only point I want to make about this is there's also dilution occurring instead of just removal, right? And this method can be used to try to estimate things like how much dilution you're getting if you don't have a flow and solute transport model, which many of us don't have for all of our sites. My point is the EC of the incoming wastewater is what, around 200, and the EC, the background, we'll take the 50th percentile. Sorry, these are percentiles along here, plotted along here, is about 800. So 200 going in to the water, 800 going out. So there's a bit of mixing you'll see occurring, and then the mixed water, where at the recovery bore is about in between at about 600. But you can calculate it a bit better than just looking on a graph. With E. coli, you'll see the fit's much better, and generally pathogens do follow a very strong log normal distribution in wastewater and environmental sampling. Again, we've got our input bore and a background bore, BG bore, and I guess where we're monitoring for compliance and looking at removals. So typically in Australia they regulate again on E. coli, and they want to get a certain log removal, and that's how the environmental regulator will look at it. So bore 219, you'll see firstly the input, you can see you've got around, here's firstly the detection limit of the system, remember it was about 10 E. coli per mil, that's around here. So you'll see firstly that all of the input data is above that, as you'd expect. So the entire set of the input data is above the detection limit. However, down here, and remember we have an upper one of 24,000 around here, and in fact some of the higher end data will also be fitted over that. What I want to get across though is, if we look at the percentiles, the 50th percentile will be, in this case, about 24,000 or something for the input water. Okay, it's all right, yeah, I know. I'm timing myself here. And you can see for both the monitoring bore and the background bore, the output, the actual 50th percentile would be fitted at around just a bit over about 10 E. coli per input. So you've already got you're guessing about 3 log removal. You can put this through sort of a Monte Carlo QMRA as well, which I've done in the paper. And in fact, yeah, a good way of determining it is you can then determine what like a removal efficiency. So you can generate a distribution like that for each one. You have one distribution minus another distribution, gives you, I guess, effectively how a distribution of the removals across each of the sites. And so I haven't plotted the whole thing here, but really what I want to point out is a couple of things. One, you can use sensor data to get better distributions than you can of a smaller data set, and it's actually more representative, and you don't have to falsify your data. Two, often people will look at the removal efficiency and quote like a mean. So this is as a percentile. So if we're looking at a mean or a median, typically means are biased towards a higher end number, of course. So I try to use a median or a 95th percentile. You can see here for Geraldton North, which is the one that Geraldton North, it has at least 2 log removal, probably 3. That's the best, but at least 2 log you can actually verify statistically that this system will give you. You can't verify more than that because you didn't find more E. coli in the groundwater. For some of them, and these are only 3 of the sites out of 17, did we actually find E. coli in the groundwater. So for the other 14 sites, you can't actually calculate the log removal, which is a problem. And people say it's 100% removed, but there's never 100% removal. It's actually technically you can't calculate it. I guess my point is also the EC. So it says 99% removal there because it's all as a percentage. Removal efficiency. EC actually grows by about 100% in this case, which is what we saw in the dilution data as well. So I guess some of that removal, not all of it, can be explained by just plain old dilution, but the rest is actually probably death and decay. Death and decay and absorption and the other processes that are going on the aquifer for removal of E. coli. I guess the main point I want to say is that out of all these sites normally, so 17 sites, E. coli is only found in 3 of the sites at the point of observation, so they're going okay. We can demonstrate at least 2 log removal for E. coli. You can do this for other pathogens as well, but of course they're much harder to find and they're much lower concentration, so you probably can't do the statistics. In the case of WA, that's considered suitable for medium level risk exposure, which is things like irrigation of lawns, irrigation of parks, and not for drinking or anything like that. And that this method is, I guess, aquifer treatment is effective in producing, without too much more work, producing a water of suitable quality for irrigation, at least by the Australian guidelines. And you don't need to go to necessarily reverse osmosis or the other high-end technologies that you do for drinking water. So we advocate a risk-based approach and a water that is fit for purpose. So low exposure waters don't need to be treated the same way as high exposure waters. So in Western Australia, for the first time, the aquifer is now actually recognised as part of the treatment train. It's actually given the same credit you'd give to, let's say, a membrane, although membranes, of course, work a lot better. In this case, we can demonstrate it's 2 log removal for bacteria. And I guess we're slowly working with the regulators and the water suppliers to demonstrate that aquifers can be integrated with engineered systems to provide a fit-for-purpose water for different end uses. Thank you.
Any question?
Yes, Jan.
And a very nice presentation. So these are already there, and then analysis was done, and then retro credited, or because people probably built wastewater treatment plants and for a long time.
Well, in case you came late, these have been around for 50 years, these ones here. They've been infiltrating in sandy soils, just boom, gone. Infiltrating for about 50 years or so. But now there's, I guess, in the old days it was looked at as disposal, just straight disposal out to sea. But now they're looking more and more at actually reusing this water as well. So they actually take the water, they pump it, and they use it for irrigation. So now they have to demonstrate, as they're using it for irrigation, or for perhaps irrigating your children's oval, that it is safe. And that's part of what this work's trying to show. As well, I have a thing about statistics that I think people do it wrong sometimes. So thank you.
More questions?
I didn't understand, is the AC in the groundwater, I think it's okay. AC in the groundwater higher or lower than
Okay, I'll show you how to read this. So these are all the values of EC. I'll take these crosses here, right? And this is the fitted line. It's not a great fit. So the 50th percentile of the EC has an EC of 800. This is the wastewater, and this is the line. And the 50th percentile has an EC of around 150, 200. So it's 800 in the groundwater and 200 or so in the recycled water. So yeah, you're getting a dilution, and the line in the middle is a mixture of the two, which you'd expect to be like that, fit between them.
So the water that's abstracted for irrigation has a higher AC than
Yes. Yep, it's about double. In fact, I've expressed these as percentages. I probably should express them as log value, but I find it difficult for logs. But this is 100% higher as a median and sometimes it's 77% higher. Sometimes it can be lower as well. But on average, as a median, it's about double, 1.2 times, 120% more.
is the AC then not too high for irrigation?
Well, depends on your crop, of course. So, AC of what? 400? That's suitable. For grass. Not for tomatoes, not for almonds, but for grass, which they're using it for the schools. That's all right. I mean, you still have to use irrigation management sometimes. And look, Australia's a really salty place. We have salty groundwater, we have salt everywhere, there's salt blowing everywhere. You're by the sea, it's salty anyway. So you probably have to use some sort of irrigation management to make sure that salt isn't accumulating within the soil. So you might use flushing techniques or things like that as well. You might also have to use calcium as an ameliorant with the soil to make sure the sodicity and the salinity don't change and the soil structure doesn't break down. But that can be done. And it's still, I think, better than ROing everything, my personal view.
Would it also be possible to buffer more water so that the system gets more compressed?
Yeah, they could do that as well. But in this example, because we're right next to the ocean, I think it'd be pretty hard. And all of these sites tend to be near the ocean because that's where everyone lives, near the ocean, because the middle of Australia is desert, there's not much there. Come over and visit. Sometime, yeah. Have lots of seals. Thank you.